So I already talked to you about electromotive force. It's the driving force for the electron transfer. It's like a waterfall. It's going from a high energy state to a low energy state. The important thing that you guys need to remember is that voltage is the work per coulomb. And so we can actually do a simple mathematical relationship where a voltage is equal to the work per charge Q, where Q is the charge. Q in this particular nomenclature is not heat. I know that you guys are used to Q as heat, as in calorimetry, but Q in this particular case is going to be the charge. So this is voltage. We can simplify this and write this expression. Okay, work is equal to, so we're just solving for this right here. And when we do that, we bring Q up here. So Q times the energy maximum is equal to, or the voltage maximum is equal to the work maximum. And you guys probably already know that as delta G, free energy. Okay. Q, charge, is equal to the number of moles of electrons times the Faraday's constant, F. So if we make this substitution for Q, we get NF and E0 right here. It's not so much important. It's not so important to derive this equation. You just have to make sure that you know how to use it. So if we substitute NF for Q here, and we substitute delta G for work max here, we have our infamous equation that the free energy is equal to, and notice there's a negative there, and because there's a reason there's a negative, is because when electrochemical potential is positive, okay, then that's a spontaneous process. Free energy is negative. Free energy is negative. And that's because the electrons are negatively charged, but that's why you have a negative sign here. So delta G equals minus NF E0, where E0 is the electrochemical potential. That is our famous equation. That's the equation that relates free energy, got to put a super zero there, to electrochemical potential. That's what you see right there. Okay. When we put a super zero above G and a super zero above E, we are at standard state. 1 molar concentration, 1 atmosphere, okay, 298. We are at standard state. So this is an important equation because now we can calculate the free energy that a voltaic cell has just based on its electrochemical potential. And that's what we have right here. So let's take a look at this example. This is an example that you might see. Usually I would allow you guys to work this out. And in the process of working this out, you guys should notice that the iron undergoes reduction. And the quickest way to see that is either the charge decrease, but when you look at this, you could probably guess that the sulfur is the one that's undergoing some sort of electron transfer. But you should also know that this second reaction is a reduction because the electrons are in the reactant side. Whenever the electrons are in the reactant side gain electrons, reduction, that's a reduction. So you have two reduction reactions here, okay? And your job is to figure out what is the spontaneous reaction, what is that voltage, and what is the free energy. at 298. Remember what I told you earlier. You want to find the combination in which one is an oxidation and one's a reduction. You can't have both reduction. You can't have both oxidation. You got to have one as an oxidation, one's a reduction, but you have to find the combination that gives you the most positive potential, the most positive value. So if we flip this right here and make this the oxidation, that'll be negative 0.77. And negative 0.77 added to 0.60 is going to be negative 0.117. That's not good, okay? Because that's going to be a negative potential. Maybe that's going to be less negative than the other, but right now that's in my mind. So I'm going to clear this up and I'm going to show you the other scenario. And the other scenario is not so much flipping this guy over, but flipping this guy over. So I'm going to keep this as my reduction, but I'm going to make my S2O6 my oxidation. And by doing that, I change the sign. This becomes positive 0.17, and that's going to be my 2-half reaction. My 2-half reaction is my iron undergoing reduction. That's 0.77. And my H2SO3 undergoing oxidation. Notice that I don't have to balance this equation unless it's asking me to balance the equation. And maybe you do need to balance this equation, and the reason why you need to balance this equation is because you need to figure out N. N is the number of electrons that are exchanged. But let me continue my thought process here. When we reverse the second reaction, that becomes negative 0.60. This is going to be a positive 0.17 volts. You notice that the second reaction is already balanced. If you look at the hydrogens, there are 4 hydrogens, there are 2 sulfurs, there are 6 oxygens. So the second reaction is already balanced. So I don't have to worry about going in there and balancing it from scratch. And then you notice that there's 1 electron on the first, there's 2 electrons on the second. I know my N is 2 right away. I got to multiply the top reaction by 2. That way the electrons cancel. So I know my N value is 2. Okay, so let's continue on. Determine the reaction that can be used as a voltaic cell. It's going to be the combination of these two. Reverse the second one, add it to the first. Calculate E0. E0 is 0.17 volts. Calculate free energy. Free energy equals minus NF E0. N is 2. F is 96,485. 2 moles of electron. 96,485 coulombs per mole electron. And then voltage is equal to joules per coulomb. So that will be 0.17 joules per coulomb. So my coulombs will cancel. My moles of electrons will cancel. I will get an answer in joules. So you take 2 multiplied by 96,485, that's Faraday's constant, and multiply that by 0.17. That'll be your free energy. And notice it should be negative. And the reason why it should be negative is because your electrochemical potential is positive. They always got to be opposite sign if they're spontaneous. So let me just show you that work real quick. Okay. There it is. Okay. This is the combination reaction. This is the voltage. This is 2 moles. I use 96,500. I usually would use 96,485 just because it's in the top of my head, but 96,500 will also work. And there's going to be a cushion in rounding off, and then 0.17 volts. Remember that 0.17 volts is going to be joules per coulomb right here. So when you do the math, it comes out to minus 32.8 kilojoules, or 32,800 joules, if you do the math. And then you guys can figure out K equilibrium, because you know that free energy equals minus RT natural log K equilibrium. So K equilibrium, actually that's log, K equilibrium is equal to E, that is natural log, to the minus delta G 0 over RT. Remember that you got to put up here 32,800 joules, because your R is in joules. So if you do that, 32,800 divided by 8.314 divided by 298, and you take the negative of that and you do the exponent, you should get somewhere in the order of 5.61 times 10 to the fifth. Why did I add 1 and 2 instead of subtracting E? Which slide are you referring to? Let me go back. Why did I add 1 and 2 instead of, what I did was I actually reversed 2, okay, and then I added it. And in the process of reversing 2, I make that a negative 0.60, because when you switch, when you make a reduction, a oxidation, you also switch the sign. Okay. You got to make sure one of them is an oxidation, one of them is a reduction. You can't have two. If you keep it like this, if you just add both of these, you end up with electrons on the both sides. They don't cancel out. You got to figure out a way that one of them is flipped so that the electrons cancel out. And you flip the one so that when you do add the two potential, keeping in mind one of these have to be the negative of whatever that value is, that it gives you the most positive. So it takes a little bit of finesse, but once you do this a bunch of times, you'll see what I mean in terms of one's got to be an oxidation, one's got to be a reduction. The oxidation, you got to flip the sign, because it's usually given to you as a reduction potential. And that's what I did here. I flipped the sign of right here. Let me clear this real quick. Okay. In order to get this, you take 1 and then add it to the negative of 2. The negative of 2 is the reverse of this reaction. Okay, that's what I mean by adding it to 2, but the negative of 2 is flipping it over. Make sure you understand the difference between thermodynamics and electrochemistry. When you flip a sign, when you flip the reaction, you give the thermodynamic value as well as the electrical chemical value the opposite sign. A positive becomes a negative becomes a positive. In equilibrium, however, remember that when you flip the reaction in an equilibrium, it doesn't become negative, because equilibrium constants are never negative. The new equilibrium for that flip reaction is the reciprocal, 1 over the original equilibrium constant. So I know that we've been flipping equations a lot in Chem 201, but you got to remember, when you flip equilibrium, then that means that the equilibrium constant is the reciprocal of the original. When you flip a reaction using thermodynamic parameters or electrochemical potential parameters, then the positive becomes a negative, or the negative becomes a positive. You're flipping the sign. So you guys should practice and make sure that you get this number. If you're not getting this number, let me know. You're probably punching in a wrong value, or you're using the wrong function in your calculator. So this is the main equation that I wanted to get to today. This is the Nernst equation. And the Nernst equation is the equation under non-standard state conditions. Remember, we had free energy under non-standard state conditions, and that is equal to the free energy under standard state conditions plus a correction term. And the correction terms is RT natural log Q, where Q is the reaction quotient for the reaction that's taking place. We can do the same thing in terms of EMF. We can put NFE here. We can put NFE here, and there's a negative in front of these. And we can put RT natural log Q here. And that is basically the derivation of the Nernst equation, but we're going to clean it up a little. We're going to divide everything here by minus NF. And now that becomes a negative. That becomes a negative. So this is going to be E is equal to E0 minus RT NF natural log Q. That right there is your Nernst equation. Notice it's a negative. And the reason why it's a negative is because over here it's a positive. Okay? For free energy, it's a positive. For electrochemical potential, it's a negative. They have to have opposite signs. You can do why would I not just divide the whole thing by the natural log by NF? Because the natural log function is its own function. You can take that answer and divide by NF, but you can't take NF in here. That would be the wrong. So just factor it out because you're multiplying by RT. So dividing that quantity by NF is the same thing. Okay, dividing that whole quantity by NF, you're basically taking this. It's basically the top term divided by NF, but you're lumping it here because all of these can be calculated separately, and then you have to calculate this separately. Okay, it makes the math easier, in other words. But yeah, you are dividing that whole term by NF, but you're usually carrying out the N natural log Q in a separate operation, and then you're using that answer to multiply against RT and then dividing by NF. It's the same math operation. Anyway, that's how this whole thing is derived. Let me just show you the derivation. Okay, we're basically using free energy and we're substituting this in. And when we do that, we have this equation. We're dividing the whole thing by minus NF. And when we do that, we get that. I apologize because this should be over here. This should be NF. This should be NF. Okay. Again, the format failed me. I want you to look at this right here because these days we have calculators that can do natural log. Ln is natural log. The inverse of ln is the exponent. Log is base 10. The inverse of log is 10 to the x. Okay. Now the reason why they have both equations is because back in the days, and this was in my lifetime, not in your lifetime, when I was in high school, we were just being introduced to the electronic calculator. And the electronic calculator was pretty cool because you can do a lot of math tricks on it. And back then we didn't have graphing calculator. We just had simple multiplication, division, and square roots, natural log. But before we did natural log, okay, people in the 50s had to use a slide ruler. Maybe you can ask your parents about that. Slide ruler, it's very difficult to do a natural log function. It's much easier to do log base 10 in a slide ruler. So whenever they derive an equation that comes out as a natural log, we put in a factor of 2.303. And when you do that basically is the value of E. okay, then you get log base 10. That's why you see both of these equations. So this 2.303 log is basically your natural log. So there's a little history for you, okay? But both are the Nernst equation. And what we do as chemists is, again, I keep telling you that chemists are generally lazy. So we're going to take this whole thing right here, 2.303 R, T, and F. And because all of those are constant, especially if we're at 298, okay, remember F is 96,485. R is 8.314. Yes, it's 8.314, not 0.08206. If we put all that and multiply it out, then you will see this equation. And again, I apologize for the format messing up, but let me clean that up for you. Okay, E equals E0, that's going to be standard reduction potential, that's generally in volts, minus 0.0592 log base 10 Q over N. And that's because N varies. N is not a constant. N depends on the number of electrons exchanged. So this right here is the equation that we use a lot of times. If we are at 298, okay, if we are at 298, the equation I like the most is this right here, because you guys can easily do natural log in your calculator, and this allows you to vary your temperature. If your temperature is 298, then go ahead and cut to the chase and use that equation. But know that all these equations are the same. You're just using different values of RT or natural log to log, things like that. But they basically give you the same ingredients. You have the reduction potential under standard state conditions, and you've got the reaction quotient here. So it's under non-standard state conditions. So when we apply this equation, and that's what you will see in the next slide, okay, you can solve many problems under non-standard state conditions. So let's take a look at this problem, and I'll sort of work this out for you in the last, say, 15 minutes. You have zinc undergoing oxidation. Okay, zinc undergoing oxidation. That's what you see right here. And then cadmium undergoing reduction. Calculate E for this right here. So what you would need to do, I know that my oxidation for zinc, because we've done this a lot of times, 0.76 volts. I just know that from the top of my head. But if you look up the reduction potential for cadmium, okay, you will find out that that reduction potential is negative, and that's cadmium plus 2 going to cadmium 0, is negative 0.403. So the potential of this cell right here, notice I've already reversed the sign because it's an oxidation, is going to be 0.76 minus 0.403. And that comes out to positive 0.357 volts. So that's the first part. Calculate the E0 for this reaction. Notice that they're all 1 molar. So that's standard state conditions. The second part is calculate the EMF for non-standard state conditions. So E is going to be E0, which is 0.357, minus RT and F natural log Q, where Q now is your products, and your products in this is going to be zinc, cadmium, but cadmium is a metal, so it's not going to be shown. That's a metal, so that's not part of the reaction. Divided by zinc, zinc is a metal, so that's constant over cadmium plus 2. So the only chemicals in your mass action expression is zinc plus 2 and cadmium. So this becomes RT and F. And notice that the electron transfer is 2 for both. So it's a 1-to-1-to-1 ratio. So the zinc concentration is up here, 0.150. And my cadmium concentration is 1.5. So let me go ahead and do that calculation for you. 0.150 divided by 1.5 is going to be about 1/10, I believe. Okay. Yeah, 0.1. And then I'm going to take the natural log of that. And that's going to be 2.303 negative. And then I'm going to multiply that by R, 8.314, and multiply that by 298. And divide that by Faraday's constant, 96,485. And divide that by 2, the number of electrons. So that comes out to, this whole term comes out to 0.0296 volts positive. And so if I add 0.357 to that, that'll be my potential under these non-standard state conditions, which comes out to be 3. Oops, sorry, I added that incorrectly. 0.357, 0.0296, 0.386, 0.387. So let's see if I'm right. I'm going to clear this up. This right here is positive 0.0296. This right here is 0.357. So we add those two up. So that's what we see right here. Okay. And indeed, when you do this, and notice I took a shortcut. I just put 0.0592 here instead of doing the whole thing. But I basically got the same answer. In my long-term calculation, because I believe I used 96,485 as Faraday's constant, but my original answer in my math was 0.3866. So 0.387. 0.387 and 0.390, it's good enough for government work. I'd accept both. And usually when it's a formula calculation, if it's within 5%, you're good. So these are the type of calculations you have. This problem right here is an interesting one. Okay, I've got about 10 minutes to explain this. So it's the same problem as before, except it's a little bit different. Okay, we still have the zinc as an oxidation, so that's 0.76. And then we have hydrogen, and we know hydrogen is 0, whether it's oxidation, reduction. So our cell is 0.76, but our cell under non-standard state conditions 0.72. Okay, that's the cell measured. That's because the concentration of hydrogen is something other than 1 molar, and my concentration of zinc is something other than 1 molar. So let me show you how this is set up so that you can see how this works. This problem is actually a very important problem because it shows you how pH electrode works. For those of you who have lab and you go in and you are calibrating the pH electrode, remember you put it under pH 4 and then you say calibrate now, and you're reading a voltage reading in logger pro. When that voltage reading is constant, you say that voltage reading corresponds to a pH of 4. Then you keep You wash your electrodes, then you stick it in pH 10. And then you watch the voltage reading again. And when that voltage reading is constant, you say, okay, that voltage reading corresponds to pH 10, and now you're ready to do the experiment. Of course, you test with pH 7. But what does a voltage reading have to do with pH? It's this problem right here. It's this problem, okay? This is how you relate voltage reading to the pH. And it goes back to this equation, E equals, we're using 298, so I'm going to use the shortened version of the Nernst equation, E0 minus 0.0592 over N. This is a 2-electron transfer. Even though hydrogen is a 1-electron transfer, zinc dictates that it has to be a 2-electron transfer. So N, in this particular case, is 2. 0.0592 log Q. Q is going to be your products, and your products are zinc plus 2 and H2. So it's zinc plus 2 and H2 over reactant, and your reactant is going to be zinc metal, which is constant in H plus. Now don't do it this way. And the reason why you can't do it this way is because I didn't go with a balance equation. If I did my balance equation, you will see that zinc going to zinc plus 2 electrons, hydrogen going to H2, and we need 2 here, and we need 2 electrons here. So this needs to be squared, okay? This needs to be squared because you need 2 hydrogens. If you're just going off the line notation and you forget the chemistry, you're going to forget that squared right there. And then you're going to be thrown off. You got to make sure that you get the chemistry right if you're going to do this problem. So we have this. We have this. Okay. So we can easily do this. We can easily do 0.76. I'm going to bring this over to the other side, minus 0.72. Okay, when I bring this over to this side, that becomes equal, and there's a negative in front of that. So I'm going to put the negative in front of that, and then that's times n, 0.0592 equals log Q. That's just simplifying the math. That's just simplifying the math. Log Q is base 10. So I can say 10 to the minus 0.76 over minus 0.72 over 0.0592 times n is equal to Q. What is Q? Q is that. Okay. Remember that I have values for H plus, I mean zinc plus, that's 0.10. I have a value for hydrogen, that's 1 atmosphere. I'm trying to calculate H plus. Where did 0.76 comes from? You guys should know that by now. We've done this so many times. Zinc to zinc plus 2. That's 0.76. Okay. We did that a lot of times. In all the examples, practically I did. The reduction potential of zinc plus 2 to zinc is minus 0.76. When we do the oxidation, it's positive 0.76. That's why I just kind of pulled it out. The 0.72 is what we measured. Anyway, this is the equation that you will use. Let me show you this real quick. A lot of this is just plain simple. Well, I won't say simple, but a lot of it is just math. So you see this equation right here? This is my log Q. When I simplify that, I basically bring my values to one side. I'm going to bring these terms to one side, and I'm going to isolate this right here. And when I do that, this is what happens. Log zinc over times hydrogen over H plus is equal to 0.72 minus 0.76, 2 over 0.0592. That was this term right here. So if you work out the math, okay, and you take this whole thing and get a number, that number is 1.351. So 10 to the 1.351 is equal to that value right here. And we're solving for this right here. We're solving for this right here. Because when we can get H plus, we can get pH. Okay. So in carrying out the math, I'll clear this out for you again. Carrying out the math, this is what we have. And this quantity right here, 10 to the 1.351, that's 22.46. So if we solve for H plus in this equation, we come up with H plus squared 0.00445. We take the square root of both sides. And when we take the square root of both sides, it becomes 0.0667. And remember, to get a pH, we need to take the negative log of your hydrogen ion concentration. Hopefully you didn't forget that. And we get a pH of 1.176. So this equation, for those of you in lab, you will see this equation again, is a very good equation because if you can do this equation right here, you understand the Nernst equation. You not only know how to calculate electrochemical potential, but you can find the concentration of a chemical that is involved in the electrochemical process. Okay, so take a look at that and make sure that you can derive it from scratch. I think you have a practice problem like this, but that's an important equation. For those of you in lab, make sure you look at that problem in your activity. I believe it's activity number 11 or number 10. I forget which one. So in summary, these are the relationship. We have a relationship between electrochemical potential, free energy, and K equilibrium. And these are the mathematical relationship that takes you from one to the other. And then in summary, we're always looking at spontaneity. When delta G is negative, it's spontaneous. When K equilibrium is greater than 1, it's moving in the forward direction. When electrochemical potential is positive, it's spontaneous. On the other hand, if free energy is positive, then the reverse is a spontaneous reaction. When electrochemical potential is negative, then you need a battery to drive the reaction in the reverse direction. And when K equilibrium is less than 1, then the reaction is not very efficient. Most of the chemical stays as a reactant. So recall that in the beginning of the semester, I told you that Chem 201 is about understanding processes, understanding chemical reactions. This is where it all comes together. All these variables are singing the same songs. They're telling you about the efficiency of the reaction. They're telling you about the spontaneity of the reaction. They're telling you about whether product is favored or reactant is favored. And so you want to be able to make sure you understand these equations and how they relate to each other. Because I believe in your next quiz, you definitely see a question where I give you one and you have to calculate the other two. And that's just using these equations.